In the first lecture we saw the definition of finite sequences, also called strings. And the second lecture we looked at infinite strings, and we saw how to put a topology on the space of all infinite strings. In this lecture we bring those two concepts together and especially see how trees capture an important aspect of the topology. So what is an infinite path through a tree? Well, let's assume we have a tree given over some alphabet as usual, and an infinite sequence over that same alphabet is called a path through T if all of the initial segments of that infinite sequence are on T. So an initial segment of an infinite sequence are up, so call it x up to n, so the initial segment of length n are just the first n entries of x, so x0, x1 up to xn minus 1. Note that an infinite path is always an infinite sequence, whereas a tree is always a set of finite sequences. So there's a difference of type here. Paths are infinite sequences, trees are sets of finite sequences. Now we use T infinity to denote the set of all infinite paths through T. So let's try to illustrate this a little bit. Let's assume we have a tree T here. Let's just put in a few branches. So now this here would be a dead branch. That means from there on there's no extension. And no infinite path obviously can go through this dead branch here. On the other hand, here we would have the beginning of an infinite path. So provided this extends further and further, this would be an infinite path because all its initial segments would be on the tree. And here is the fundamental fact that connects the tree, infinite path through a tree, to the topology on the sequence space that we defined in the previous lecture. Namely, a set of infinite sequences, so a subset of the sequence space over A, is closed with respect to the product topology if and only if there exists a tree such that the set of all infinite paths through T is precisely our set F. Let's try to prove this. So we start with the only if direction. So suppose we have a closed set F, and being closed means that the complement of F is open. So let U be the complement in our sequence space A to the n. And by definition of the topology, this means that U can be represented as a union of basic open cylinders. So each of these cylinders in this union is generated by a string sigma, and these strings sigma are collected in a set S. So S is a set of strings, and together these strings generate the cylinders that represent our open set U. To facilitate our lives a little bit, we use the following notation. So we extend the notation from cylinders to sets of cylinders, so to say. Namely, by just saying square bracket S means that's the open set generated by the strings in S. So in this illustration here, this would be a string in S, this would be a string in S, this would be a string in S. And all the extensions, the infinite sequences that extend any of those strings, go into U. So each of these cylinders together, all of these cylinders make up our set U. So the basic observation now is the following. Well, F is the complement of U. So the sequences in F are the ones that are not contained in any of those cylinders here. Well, which means that somehow we can find their way through through a tree without running into one of those cylinder sets here. Well, we collect all these things in a tree, and then the set F will be precisely the set of infinite paths through this tree. So, idea: collect all the strings that do not run, that are not kind of covered by one of those cylinders here. Let's try to do this formally. So we have X is in F if and only if it is not in U, which is precisely the case if and only if it is not no sigma in S is not is an initial segment of X. Now we define a tree T by putting a string into T if and only if there is no string in S that is an initial segment of tau. So we put tau in T if and only we cannot find a string sigma in S that kind of covers it, that is an initial segment of tau. You should take a moment to verify that this condition here indeed does define a tree. So now see, let's verify that this tree actually works or does what we want. So assume we have an infinite sequence, an infinite path through T. Well, that means all initial segments of that sequence are in T. Well, by definition now of T, this means that for all n, we cannot find a sigma in S that is an initial segment of X up to n, the length n initial segment of X. Well, that's logically equivalent to, for all n and for all sigma in S, sigma not being an initial segment of X up to n. Well, that in turn is equivalent to this condition. You're saying that just for all sigma in S, sigma is not an initial segment of X. And there the reason is simply that in order to be an initial segment of an infinite sequence, you would already be an initial segment of a finite initial segment of that sequence, right? So this is how we get from here to here and back. But now let's look at this. This just says that X is not does not extend any of the strings sigma in S, but that means by definition it is not in the open set generated by the strings in S, which by our assumption is just the set U. So this is equivalent to X not being in U, but that's, since F is the complement of U, means X is in F. So now we do the other direction. So for this, suppose that our set F is given as the set of infinite paths through a tree T, and we can, without loss of generality, assume that T is not empty. And we have to show that the complement of F is open. So let's denote the complement by U. So for this we have to show that U can actually be represented as a union of cylinder sets. And we for that purpose we define a set S, which is a set of strings, in the following way. So we put the string sigma into S if and only if sigma is not on the tree, but if we delete the last entry of sigma, this and call that resulting string sigma minus, that string is on T. So for instance, if sigma is sigma 0, sigma 1, up to sigma length of sigma minus 1, then sigma minus would just be the same string with the last entry deleted. So let's look at an example of how S is defined. So here we have our tree T. So we assume these dotted lines just indicate that there the tree still extends and goes on. But now how do we find S? Well, in a string is in S if and only if it is not on T, and if it's the kind of the longest proper initial segment of sigma is on T. So for instance, this string here, right, this is on T. So now any extension of this, right, that's like this here, this would be go into S. So this string here, sigma is in S, right? And this would be sigma minus, and this is in T, right? But the extension itself is not on T. Likewise, this extension here, so this string would be in S, as would this string here, and this string here. So the green strings that are marked green here indicate strings that have to go into S. So now it's actually not hard to see that S does the job for us, namely it induces U as an open set that is a union of the cylinders or strings contained in S. So let's assume X is in U. That's the case if and only if, of course, by definition, if X is not an infinite path through T. Well, if X is not an infinite path through T, then at some point it must stop being a path through T. So then that means there exists a minimal length, so that at that length the initial segment x up to n0, so this is the initial segment of x up to of length n0, is not in T, right? Because x is not an infinite path, so it stops being a path, and so there must be a minimal point where it stops being a path. So now this is equivalent to, since n0 is chosen minimal, and provided T is not empty, that the next shorter or next longest initial segment of x is in T, right? Because n0 again is chosen minimal with this property, right? But now these two conditions together, right, exactly constitute that x up to n0 is in S, because x up to n0 is not in T, but its immediate predecessor is in T. So that means x is in x up to n0 is in S, which then now implies that x is in the open set induced by S, namely the union of open cylinders induced by strings in S. And from this we can conclude now that U is in fact equal to the open set induced by the strings in S. So union is U is a union of cylinders, and hence U is open. That's exactly what we wanted to show.